Welcome to part 2 of our discussion of statistical process control lecture. And in this case, we'll continue our discussion from control charts for variables. And in this case, in this area, we'll be looking on range chart, which is the R chart, which is plots for the variability, as well as the mean chart or X bar chart, which plots the sample averages. And in this case, if you were to, we can do an X bar chart for standard deviation that is known. In that case, it's pretty straightforward. X bar plus Z times standard deviation of X. So where X bar is the grand average, X bar of all the averages divided by the number of samples that you're taking. So in this case, you can easily find, you have the process standard deviation and take the process standard deviation, take a square root of n of that to come up with the process standard deviation of sample means in this case, and come up with the value. In this case, an example, very quickly, you can see, just for illustration purposes, you have 10 different samples, and in each sample, you're collecting 5 data points. So maybe it could be the diameter of the slip ring, in this case in centimeters. So in this case, you find out the first 5 slip rings that were collected in the first sample had diameters of 5.02, 5.01, 4.94, 4.99, 4.96. So given that averages out, those 5 numbers average out to 4.98. Similarly, second one averages to 5 exactly even. The third one averages to 4.97, then after that 4.96, and so on. All the way till the 10th sample, which is 5.03. When you add these up, that comes out to be 50.09. And if we know the process average standard deviation is given to be as 0.08, given this number, and the total of all the averages is 550.09 divided by 10 as we proceed, that gives you the process grand average, average of averages, which is 5.01. So this is the 5.01 plus the z of 3 as by default times take the standard deviation of average means, which is 0.08 divided by square root of 10, and that will give you, after the calculations are done, this will be 5.09. When you subtract the same thing, it gives you the calculation of 4.93. So in that case, you can easily check to see if every single X bar value falls between 5.09 and 4.93. In the case of, so there are X bars that can be created, but in this case, standard deviation is unknown. So in this case, the formulas requires, instead of standard deviation, to use R bar, which is the standard range value. Range is maximum value minus the minimum value. Okay? And so in this case, we actually use the 2 constants which are taken from a table, A2 and which is being provided from this control chart factor. So one of the factors is A2, which is used for X bar chart. And then we have 2 different factors which are used for R chart, D3 and D4. So this is the table that is given in the textbook. And that's what is used for a specific sample size. In this case, if you have a sample size of 5, you will have the factor A2 to be 0.577. So going back, we are looking at the same slip ring example, a numerical example where we had a slip ring diameters that range, we are taking 10 different samples of 5 slip rings each. And in this case, we already calculated the range X bar values in the previous example. The total added up to be 50.09. But the range in this case is the maximum, which is 5.02, minus the minimum, which is 4.94. Subtract that, it gives you 0.08. Same way you calculate it for the rest of them. The last one is 0.10, which is taking 5.08 minus 4.98, which is maximum minus minimum. That's 0.10. So if you take add these up, this is 1.15. So in order to calculate average of this, which will be take the total, divide by number of samples, which is k is 10. So you take a 50.09 divided by 10, and in this case, R bar will be 1.15 divided by 10, and that is the numbers that you have up here. So you already have X bar, which is 50.09 divided by 10, 5.01, and R bar is 1.15 divided by 10, which is 0.115. So once you have these, and as I said, take the A2 factor from the table, which is 0.577, which is rounded over here to 0.58. Plug that in, and you get the values of 5.08 and 4.94. So using those, you can easily plot the X bar chart to see if things are out of control or not, and you can see one of the value is in fact out of control, plus this is not random pattern. So X bar chart is definitely not in control in this case. Now for this scenario, we can use the R chart also, and that the values of D3 and D4 are being obtained from the same chart that I mentioned earlier, where you are actually providing. So for 5, you have D3 is 0 and D4 is 2.114. That is being looked at in this particular case. So in this case, all you are doing is multiplying those values to the R bar, and in our case, those are the numbers that you had for the slip ring diameter example, and upper control limit of R bar is 2.11 that I mentioned earlier times 0.115, which is 2.243, and lower control limit is 0 by multiplying with 0.115. And so in this case, given that, you can easily calculate the R chart. So you can see this variability is within statistical control. So R chart exhibits that from the variability point of view, the data is in control, but averages don't seem to be in control. So that definitely has to be remedied in this case. So these two charts have to be used together in many cases, because you can't really make sense of averages without the range. So process average and variability must be in control. Both of them have to be controlled in order for the data to be in control, in order for the process to be listed as statistical control. So sample can have very narrow ranges, but sample averages might be beyond control limits. So in this case, or sample average may be in control, but ranges might be out of control. An X chart, an R chart might show a distinct downward trend, suggesting some non-random causing reducing variation that you have. Various type of control chart patterns that you need to be aware of is run, that you see a consistent downward movement or upward movement. So that is sequence of sample values that display the same characteristics. Something very similar to what you may see in Dow Jones Industrial Average, as if it consistently goes up or consistently goes down, that will be a run. So certain pattern determine if observation within limited control chart display a non-random pattern. That is, if things are not don't appear to be random in this case. So to identify a pattern, there are certain rules of thumb, heuristics that are available. 8 consecutive points on one side of the center line, that's not random. 8 consecutive points up or down, consistently going up or consistently going, that also is not random. 14 points alternating up and down, oscillating, like a pendulum along around the average, that also is not random. 2 out of 3 consecutive points in zone A on one side of center line, which I'll show you, which is typically, and then 4 out of 5 on the zone A or B that you have. So in this case, let me go into the details of So if these, you can see, these are not random because most of these data points are in below the center line. And these are all consistently above, so these are not random. Whereas this shows a run where consistently items are going above, whereas over here what we are measuring is consistently going down. And here comes the zone for pattern test. So remember we, in upper and lower control limits, we are calculating plus or minus 3 standard deviation. So this is 1 standard deviation, this is 2 standard deviation, and this is plus or minus 1 standard deviation. This is plus or minus 2 standard deviation, and all the way till that's plus or minus 3 standard deviation. So this is the first standard deviation, plus or minus is just the zone C. Plus or minus 2 standard deviation now includes zone B, and then plus or minus 3 standard deviation is the zone 3. And in this case, you can see if things are falling in 2 out of 3 are falling in zone A, that's a problem, and 4 out of 5 are falling in zone B, that's also not, acceptable. So you can easily perform a pattern test to see if things are falling in what zone they're falling in, and accordingly make an evaluation in that case. Okay. So as I mentioned earlier, 4 items falling in zone B out of 5, that could be an issue. 2 out of 3 in zone A, that could be an issue in this case. Okay, sample size determination. Attribute charts require larger sample size. So typically you have a huge number of parts, whereas a variable chart requires smaller samples because that's where the range chart is done quickly so that you can process things. So that will take fewer samples. Now let's talk about the last topic of our discussion in statistical process control, which is the process variability. Rather important concept in statistical process control. It basically tends to compare natural variability to design variability. And what I'd like to call, basically comparing, so process basically looking at voice of the customer and comparing that with the voice of the process. Okay, and those are the 2 voices that we have mentioned earlier as to what customers want, what they will consider acceptable versus what our process is capable of doing. So those are the 2 things we are comparing and finding out if the process capability measure is up to par to what is demanded in the market. So in this particular case, so that's what we are comparing, the natural variability, which is the natural variability of the process, with design variability, what the design specifications that are provided by the customer. Okay? So natural variability, what we measure with the control charts, which is plus or minus 3 standard deviation. When you go plus 3 standard deviation on this side and minus 3 standard deviation on this side, altogether it's a total of 6 standard deviations is the range that you're looking at. So in this case, that's what you're looking at in terms of natural variability. And design variability is coming from tolerances, design specification reflecting product requirements. So you typically may have a customer say, I'll accept anything 9 ounces plus or minus 0.5 ounces. So in that case, you have tolerances of plus or minus 5.5 ounces that is allowed or acceptable. So in this case, you have process capability. So in example A, your design specification that the customer has provided are very narrow. That is the customer expectations are pretty high in terms of what the demands for quality of the product is. Whereas what you're offering in terms of process is too variable. The process output is so variable that most of the items that are falling either below what is acceptable minimum or outside more than what is considered maximum, because this is the area where it will not be acceptable. Now, So in this case, when natural variation exceeds design specification, process is not capable of meeting specifications all the time. On the other hand, you're looking at design specifications can easily be accommodated by the process variability. So in this case, design specification, our natural variation is the same. In this case, process is able to meet the specification most of the time, which is 99.74% of the time. And then you have the third scenario where design specifications are much looser, customer is much more accommodating, but you have a very tight specification of natural variation. That means your process, maybe it's a brand new machine and it doesn't have too much variability, which is a good thing. So you can more than do an extremely good job of providing, conforming to specification. It will always conform to specification, given the fact that even if the machine were to be, staying in here, majority of almost all the products that is being produced are within the design specification. So that is where the design specifications are greater than normal natural variation. But sometimes if the things are off-center, what will happen is, even though the process natural variation is less, but because of the off-center nature of it, the specifications, even though design specifications are greater, but the process is off-center, it is not capable of producing some output which will be not meet certain or either upper or lower specification, and that is something that easily can be fixed. And so let's look at how this translates into the various metrics we have. So let's look at the first process capability ratio that we mentioned earlier in terms of voice of customer and voice of process. So in this case, the voice of the customer is the tolerance ranges, what customer is willing to tolerate on the maximum and the minimum, and the natural variation or the voice of the process is what the maximum and the minimum that is offered by the process in this case. As I said, it is plus or minus 3 standard deviation, which comes out to be the difference between plus 3 standard deviation minus 3 standard deviation, which is total of 6 sigma. And on the numerator you have is, in this case, upper specification minus lower specification limit. And in this case, in terms of computing CP, let's look at a numerical example. And the net weight specifications are 9 ounces plus or minus 0.5 ounces. Process mean is 8.8 ounces that your process is normally on average producing. And standard deviation is 0.12. So if this is the sigma, 6 times sigma is 6 times 0.12, which is the denominator. And plus or minus 0.5 ounce when added to or subtracted from 9, which will give you 9.5 minus 8.5. So you have 10 divided by 0.72, which gives you 1.39. So if your CP is greater than 1, which gives you in control process. Now let's look at the second part, which is the process capability index. This comes into play when any time the process is off center. If you recall, we mentioned over here the average that the customer, ideal target the customer wishes is 9 ounces, but your process is off center when you're producing 8.8. So in that case, it is meaningful to see if, because in theory you are capable 1.39, but the question is in reality, because of this off center nature, are your process still delivering delivering or is capable of providing a product that is within specifications. So if we look at process capability index, what we are doing is, earlier, what we are trying to get a sense of is, if this is the variability, this is minus 3 standard deviation, this is plus 3 standard deviation, and what you really want to, and if this happens to be design specification, and this is the mean, okay? And mu. And what we really want to find out is if, in fact, if this is the upper specification limit, let me just erase this part. And this is the upper, lower specification limit, and this is the upper specification limit. So what we want to make sure is what is this portion versus what is this portion. So over here, it appears that we are more than, upper specification limit is more than the, this part. So this natural variation is well within the design specification, but this part is the negative side. So that is going to be a problem. So this much portion of the product that is being produced is because of off-centering on this side, it's outside the lower specification limit. So that is what we want to find out. So in this case, what we really need to do is take the x bar bar minus the lower specification limit, which if I were to take the x bar bar and minus the lower specification limit. So what I'm trying to do is find this number. So this is x bar bar minus LSL. And the second part is USL minus x bar bar. So what I'm trying to see is if this one, how it compares to the 3 sigma over here. Which one is bigger? Because it seems like the 3 sigma over here is bigger than the, so that is going to be not capable on this side. Whereas this one is definitely larger than the 3 sigma that is going to be capable. Okay, so but let's look at that in this example. So go back to this example and compute CPK. You'll notice that in this case we take the minimum, which is going back in here. What you're interested in, which one is more critical, which is the minimum. So in this particular scenario that I showed you, this portion, the numerator is smaller than the denominator, and that's what we want to find out, which one of them is minimum. So x bar bar minus LSL, lower specification limit, divided by 3 sigma, and upper specification limit minus x bar bar divided by 3 sigma. So if you take this one, this comes out to be 8.80 minus 8.50, which is a total of 0.30 on the numerator, divided by 0.36. So you have 0.30 divided by 0.36, that is less than 1, because which comes out to be 0.83 basically. The second part is 0.70 on the numerator divided by 0.36. That's definitely over 1. But the minimum of these two is the 0.83. So that makes this process not in control. Even though in theory it is capable of delivering a process that is within the design specification, but because of the off-centering, it is not going to be doing it. So that's where one has to look into and see, you have certain things that one can do, which is in terms of SPC and process variability. One can easily, in the first case, when you have your specification limits are tighter than process variability, you can try to reduce the process variability by acceptance sampling. Some bad units may be accepted, and that may hurt your bottom line. But over here, in the case where you are a process is delivering exactly what the customer wants, you can easily use statistical process control to keep the process in control. And in this case, you are well within the range. CPK is greater than 1. That means the process is very capable of delivering a good quality product. So design a process that is, it's in control and maintain that. That's the ideal part. So that pretty much wraps our discussion for statistical process control in this lecture. And we'll see you next time with another discussion on operations management topic. Thank you.